In this video, we will be performing stoichiometric calculations from balanced equations, and we start with a review on how to read a chemical equation. So in here, we are given this balanced chemical equation, and this is trying to tell us that four molecules of ammonia, or NH3, reacting with five molecules of oxygen gas will be producing four molecules of nitrogen monoxide and 6 molecules of water, or 4 moles of ammonia and H3 will react with 5 moles of oxygen gas to produce 4 moles of nitrogen monoxide and 6 moles of water. Now take note that the coefficients here in the balanced chemical equation tell us the relative number of moles of each element or each compound present in the reaction. All right, so if we are going to get the ratio between the number of moles that are reacting, for example, for ammonia and oxygen, then we say that 4 moles of NH3 is to 5 moles of O2. All right, so we just base it on their coefficients in the balanced equation. So what is the mole ratio between O2 and NO? So that is 5 moles of oxygen is to 4 moles of NO. All right, or if you are asked what is the ratio between nitrogen monoxide NO and water, so we say that there are 4 moles of nitrogen monoxide reacting with 6 moles of water. All right, and we can use these mole ratios to perform a series of steps such that we'll be able to deliver a stoichiometric calculation. So it so happens that, for example, we will be given a certain amount in one of the reactants, and we will be asked how much of the products will be produced. So as long as you have your balanced chemical equation and the amount in grams or in moles of any particular compound in the balanced equation, then you can find out the rest. All right. So most common calculation involves converting the mass in grams of substance A into the mass in grams of substance B. So, for example, you are given 10 grams of ammonia, and then how many grams of water will be produced given 10 grams of ammonia. All right, so that is uh, our ammonia here is our substance A, and water is our substance B. So if we want to get the mass in grams of water from 10 grams of ammonia, then we will have to follow the series of steps. All right, so first is we get the number of moles of substance A, and then by using the mole ratio, we cancel out the moles of substance A and end up with the moles of substance B. And after that one, we convert the moles of substance B into the mass in grams of substance B. And then I hope that you are familiar how we convert mass in grams to the number of moles, or from moles into mass in grams. We just use the molar mass. All right. So using the mole ratios, we can do the following calculations: mole to mass, and mass to mass. So those are the most familiar calculations that are involved in stoichiometry. So let's have the first part, mole to mole conversion. All right, let's see. So here we are given an example in the following reaction: 6 moles of octane, given by the formula C8H18, is completely combusted in oxygen gas. Okay, so there's a reaction between octane and oxygen gas. So if you remember the types of chemical reactions, this is a combustion reaction. Octane is a fuel, a certain fuel. Once you provide enough energy for it to react with oxygen in the air, then you end up with fire. Okay, you end up with burning. So that that process produces carbon dioxide and water. And then you are given here the whole equation and the balanced chemical equation in itself already. So here we are asked how many moles of carbon dioxide and water respectively will be formed. All right, so we start with carbon dioxide first. Now, first thing to do for answering stoichiometric problems is to make sure that the equation is already balanced. All right, so we really have to check whether there is equal number of atoms in the reactant side and in the product side. So for example, in here, let's say we want to get how many moles. We are asked to determine how many moles of carbon dioxide and water there are. So let's have number of moles. This is what is asked in the problem. So we will write it down so that we will be guided. So number of moles of carbon dioxide is, again, we are given one of the reactants, which is octane, the number of moles. Okay, we have 6 moles. So we start with what we have. This is 6.0 moles of C8H18, right? So it's good if we try to complete our units with the corresponding label so that we won't get lost. All right. Now we are given 6 moles of octane. So the first thing that we have to do is to convert, or we want to convert it into a mole of substance B. All right. So do you think there's a need for us to get the molar mass of C8H18 is there? This is 18. So not anymore. Okay, we can use directly the mole ratio. So in here, the mole ratio between octane and carbon dioxide is that 2 moles of octane are needed in the reaction to produce 16 moles of carbon dioxide. So since we want to cancel out C8H18, the octane must stand by our denominator side. Okay, so in here we have 2 moles of C8H18, right? And on top is our carbon dioxide, the number of moles of carbon dioxide, which is 16. So that's 16 moles of CO2, right? Now we can cancel moles of C8H18, or we can cancel moles of octane. Now we end up with the unit moles of carbon dioxide, which is what we want. So we carry out the operation. That's 6 times 16 divided by 2. All right, so we end up with the answer of 48 moles of carbon dioxide. Meaning to say, if we have 6 moles of octane, upon complete reaction or complete combustion, then we will be able to release 48 moles of carbon dioxide. And that's practically a big number. Okay, that's why we have to keep track of our carbon dioxide emissions. And then we also have, we are asked for the number of moles of water. All right, number of moles water, H2O. So still, what was given in the problem is that we have 6 moles of C8H18. So 6.0 moles of octane. That's H18. So Again, no need to get the molar mass. This is purely mole to mole conversion, okay, or mole to mole relationship. So, what is the mole ratio between octane and water? So, again, where do we find the mole ratios? We have to find it based on the coefficients in our balanced chemical equation. So, since we want to get rid of octane, then we follow the conversion factor, that's 2 moles below as our denominator, 2 moles of C8H18, and then on top should be what? On top is the number of moles of water, which is practically 18 moles of water, alright? So here we have 18 moles H2O. So we can cancel now on the number of moles of octane so that we will end up with the number of moles of H2O. So that gives us 6 times 18, then divided by 2, right? So we have 54 moles of water. Okay, so it's good if we complete the units with their corresponding labels and then make sure that what we ended up with as our final answer is what was asked in the first place. All right. So in here in the reaction, if we are given 6 moles of octane, then there will be 48 moles of water, or 48 moles of carbon dioxide rather, and 54 moles of water. All right. So let's try to box it out properly. Okay. So maybe a few minutes to absorb what has happened here again. Or what we use are the mole ratios between the compounds, the given and the asked compound. Okay, that is for mole to mole conversion. So if you remember, what we did was just cover the moles of substance A, use the mole of substance A, cancel the number of moles of substance A by using their mole ratio so that we will end up with the moles of substance B. So this is now a mass-to-mass relationships. Okay, so in the following reaction, 690 grams of octane with the given molar mass of 114.26 grams per mole is completely combusted in oxygen gas with a molar mass of 32 grams per mole. How many grams of carbon dioxide with a molar mass of 44.01 grams per mole are formed? Okay, so you have now the balance equation given, right? Sorry. So let's start with what we have. Okay, in here we are asked how many grams of carbon dioxide. So this is quite a long process already, since we will be converting mass in grams of substance A to mass in grams of substance B. So number of grams of carbon dioxide is equal to, we are given here 690 grams of octane. So 690 grams of C8H18. So this is C8H18. So take note that before we can use the mole ratios, we still have to convert grams of octane into the moles of octane. Alright? And we can use the molar mass of octane. So if I want to get rid of the unit of grams, so place grams at the bottom of the conversion factor, or okay, below the line. So 114.26 grams of octane, C8, H18 here. And then on top is your moles of octane. So mole C8, H18. Alright, so again, we are using the molar mass of octane to get the number of moles of octane. So we can cancel this out, cancel this. Now we have the number of moles of octane. After getting the moles of octane, what's the next thing that we have to use or to add as a conversion factor? It is the mole ratio between carbon dioxide and octane. So we need to get the moles carbon dioxide. Okay, and I hope that you understand why we place this as our numerator. Okay, so we wanted to cancel out moles of octane, mole of C8H18. Alright, so and then where do we find the mole ratio? We can find it from the coefficients in the balanced chemical equation. So in here, let me just add one more parenthesis. So the mole ratio of between carbon and octane is 16:2, right? So the coefficient of carbon dioxide is 16 here. I mentioned carbon only a while ago. It's actually carbon dioxide. Okay, so 16 moles of carbon dioxide and 2 moles of octane. Okay, so we can cancel the unit of moles octane, and we end up with moles of carbon dioxide. So now that we have the number of moles of carbon dioxide and we want grams of carbon dioxide, we add another conversion factor that will give us the gram CO2. Alright? And that the mole CO2 will be cancelled out. So what quantity is this that we are using? What do you think? So this should be our molar mass. Alright? So the molar mass should be used to convert moles CO2 into grams of CO2. Okay? And thankfully it was already given. However, if it were not, then we will have to find it out ourselves. Okay? So this is 44.01. Let me just place the label. I'm quite OC that way. Okay, so right now we can cancel moles of CO2, cancel moles of CO2. Now, if everything else got cancelled and we already have the unit that we want, then we can start inputting in our calculator. So that is just 690, all right, divided by 114.26, okay, times 16 divided by 2 times 44.01, and then divided by 1, but that we don't mind it anymore. So that gives us 2,126 grams of carbon dioxide. Okay? Now, you might have noticed that we exceeded the actual number of significant figures in our answer. So one thing that we could do here is to use scientific notation. So in the scientific notation, we can just end up with 2 point. Since this is 126, then we can round this off into 2.1. So now we have, in the given, we have 2 SFs, 2 significant figures. So in the final answer, we also have 2 significant figures. So we may stop at 2.1, yeah, times 10 to the power of, how many places did we move? 1, 2, 3. So 3 decimal places, and then grams of carbon dioxide. All right? So that's practically mass to mass conversion or mass to mass stoichiometric calculation based on what is given in the problem. All right? So maybe a few minutes for you to reflect and absorb. Okay, just take note of what happened in here. So we are given the grams of octane. We use the molar mass. Okay, we use molar mass to get the number of moles of octane. After that one, we use the mole ratio to cancel out moles of substance A. And then again, we use the molar mass of substance B, right? So let me just write down sub B here, okay, which is our final, which is our ask, and then here, which this is our given. All right. So the process really came from mass in grams of substance A down to mass in grams of substance B. All right. So we'll stop here for now. You can take a break or